Today we're going to look at Putnam problem A3 from 2022. The problem says, let P be a prime number greater than 5, and let f of P denote the number of infinite sequences such that the terms in our sequence are all taken from the integers 1 through P minus 1, and the terms in the sequence satisfy the relation shown here, which says that the product of terms two steps apart from each other is congruent to 1 plus the term in between mod P. We want to prove that f of P, that is the number of these sequences, is congruent to 0 or 2 mod 5. It's a good idea to construct an example to make sure you understand the problem. Let's say P equals 7. Now f of 7 will be the number of infinite sequences with terms taken from the set of integers 1 through 6, such that for all n greater than or equal to 1, a sub n times a sub n plus 2 is congruent to 1 plus a sub n plus 1 mod 7. This condition being satisfied, together with the fact that all terms in the sequence must come from the integers 1 through 6, implies that we can find a sub n plus 2 from terms a sub n and a sub n plus 1 by the following recurrence relation. Essentially, once we've picked a1 and a2, the rest of the terms in the sequence are determined. Here's an example of one of these sequences. More generally, it'll help you to view the numbers in our sequence as being taken from the field of integers modulo p. Back to the problem, we're being asked to solve that f of p is congruent to 0 or 2 mod 5. But that only makes sense if f of p is finite. It turns out that f of p is finite, and the reason is that we have a finite number of terms to choose from for the first two initial terms, and then the rest are determined from those. So f of p will be at most p minus 1 squared. Now, to count the number of sequences, finite or infinite, that satisfy our condition, the answer is very simple. It's just p minus 1 squared. However, that's not what the problem is asking. The problem wants the number of infinite sequences. Recall that we are not allowing terms that are 0 mod p in our sequence. However, for certain choices of a1 and a2, we will eventually get such terms, meaning we don't get an infinite sequence of solely integers from the set 1 through p minus 1. That means it's sufficient for us to count the number of choices a1, a2 that produce a sequence with no members that are 0 mod p. It would help if our sequences were periodic with some period n, so that we could check only the first n terms and make sure that they are not 0 mod p, which would prove that we have an infinite sequence of integers taken from the set 1 through p minus 1. What's interesting about our example for p equals 7 is that the sequence has period 5. We might guess that all sequences could have period 5. So let's try writing out the first 7 terms of an arbitrary sequence in terms of its initial terms a1 and a2 and see whether the 6th and 7th terms will match the first and second terms, in which case we'll have proven the desired period of 5. The initial terms a1 and a2 we pick arbitrarily. The third term we find using our recurrence relation, performing division and addition mod p. The fourth term we find in the same way, and use our work for the third term to simplify. We do the same for the 5th, 6th, and 7th terms of the sequence. Again, we're assuming none of the terms are ever 0 mod p. Now, notice that a6 equals a1 and a7 equals a2, which together with the recurrence relation mean our sequence is periodic with period 5. Since our sequence was arbitrary, this is true for all of our sequences whose terms are taken from the set of integers 1 through p minus 1. So which choices of a1, a2 produce a3, a4, a5 that are still in the set of integers 1 through p minus 1 modulo p? Well, a3 is congruent to 0 mod p if and only if a2 is congruent to p minus 1 mod p. A4 is congruent to 0 mod p if and only if A1 plus A2 is congruent to p minus 1 mod p. Finally, A5 is congruent to 0 mod p if and only if A1 is congruent to p minus 1 mod p. We now have to count the number of pairs A1, A2 that do not satisfy these conditions. We know we have p minus 1 squared total pairs A1, A2, which are visually represented as entries of the table seen here, which holds all possible sums of A1 and A2. Excluding the case where A1 or A2 are congruent to p minus 1 mod p, we end up removing the last row and column of the table. Excluding the case where A1 plus A2 is congruent to p minus 1 mod p, we end up removing this diagonal, which has p minus 2 entries. Subtracting the number of entries removed from p minus 1 squared, we get the following for f of p, which factors to p minus 2 times p minus 3. Now remember what the problem is actually asking us to do. We want to prove f of p is congruent to 0 or 2 mod 5. In the typical fashion of these problems, we can separate this into cases because we know that p is either 1, 2, 3, or 4 mod 5, because p is prime and greater than 5. In the case p is congruent to 1 mod 5, we get that f of p is congruent to 2 mod 5. I encourage you to do the rest yourself. Here they are. This is all of the cases, so f of p is proven to be congruent to 0 or 2 mod 5. To finish the video, let's summarize what we did in this problem. We wanted to prove something about the number of infinite sequences that satisfy some property. As with all Putnam problems, you want to do an example first to get an idea of what kind of object you're working with. Next, we know the number of sequences with our desired property is finite because the initial terms completely determine the rest of the terms, provided our second property that no terms are not 0 mod p are satisfied. We then show that our infinite sequences are periodic, so we only have to check a finite number of terms to be not 0 mod p. Using our expressions for the terms in the first period of the sequence, we count the number of initial values that ensure the property of not being 0 mod p. Finally, we prove this number is congruent to 0 or 2 mod 5. That's all for this video. Thanks for watching.